All right, so we're going to talk about functions today, the first section of chapter 3, the beginning of everything. So we're going to start out by talking about functions, and a lot of the stuff in this section are things that you've done before, and then there's some pretty important things in here that we're going to do pretty much the rest of the semester that you need to latch on to. So let's start out with some easy stuff. So a function is based off a relation. And a relation is just a correspondence between two sets. For us in an algebra class, it's normally the domain and the range. Okay. Domain, remember, is x values. Range, remember, is y values. Sometimes you'll see them talk about input and output, but typically x and y are the way we deal with the domain and the range. So those are going to be important terms for this section, and pretty much the entire course is domain and range. We're going to deal with domain and range for all the different types of functions that we're going to work with throughout the semester. So when we talk about domain and finding the domain and things, especially domain, we do some range, but mostly domain. Definitely pay attention to the things that we've got to know for that. So those are going to be important terms. So a relation, an example of that, we how do we normally write a relationship between x and y in an algebra class? What's the most basic way? Maybe here's a hint.
An ordered pair.
Ordered pairs. That's the most basic relationship we have. We have more advanced ones when we get into equations and things like that, but the most basic relationship we have between x and y, or domain and range, is the ordered pair sets. Okay, so x and y, example of that might be, we got a relation. It's a set of ordered pairs: 3, -2, 5, 6, -7, 8. And I'm just making that up. It's not coming from anywhere. It's just a made up set of ordered pairs out of that. And that's a relation. Now, to decide if a relation is a function, there are certain rules that have to be in place. And heard some of y'all talking about this earlier when I told you what we were going to be doing. A function, and when we're dealing with functions in college algebra, it's from x to y, because there are other types of functions. That's the from x to y, it associates each x with one. And the shorthand way of remembering that is it doesn't repeat what? X's. It can repeat y's, and that's okay, but you cannot repeat x values to be a function. So a relation is a set of ordered pairs. A function is a special relationship between ordered pairs, and the x's don't repeat. That's the difference in a relation, just a set of ordered pairs, and a function, is that x's can't repeat and be a function. Okay, so we're going to play the game. Is it a function? And I'm going to use letters to do my examples with, because that's what I use a lot. So. All right, so we'll start with just a set of ordered pairs. 2, 3, -3, 5, 6, 4, and 8, -2. Is that set of ordered pairs, is it a function?
Yes.
Yes. Okay. There are no repeated x values, so it passes. It doesn't matter if they're repeated y values. We don't care if that's happening when we're just trying to test if it's a function or not. So this is definitely a yes. It is a function. Let's look at another set of ordered pairs. -3, 7. 8, -1. -2, 7. 8, 0. Is that relation a function?
No.
No, why not?
It's the 8.
So, repeated x values. So if it's not, we need to know why. And I'm just going to circle those to show that, hey, those are the two that are repeated. It doesn't matter that that 7 in the y value position is repeated. That's okay. To be a function, x is the only thing you cannot repeat. So be careful of that. Y's are okay as long as the x's don't repeat. All right. So relations can be represented as sets of ordered pairs. They can also be represented in what's called a mapping. And a mapping has a domain bubble and a range bubble. And they'll have some numbers in those: 3, 5, 7, -2, 6. And the mapping is just they draw arrows to create the ordered pairs. So like 3 to 6 is the ordered pair 3, 6. And then 5, -2. Let's do 7, 6 as well. And we have to decide, is that a function or not based on the mapping. So we see two arrows going to the same range value, but range is what? Y. Is it okay for Y's to happen twice? Yeah. Are there any of the X's have two arrows coming from them? No. So is this a function? Yeah. So with the mapping, we're just looking to make sure there are not two arrows coming from the domain bubble from the same, we'll call it a node in there. That's really what it's called. But let's do another one of those. Domain, bubble, range, bubble. 3, -5, 8, 7, -9, and 10. So the mapping draws the arrow from 3 to 7. Let's do -5 to 10, 8 to -9, and then 3 also goes to 10. So this would be an example of a mapping that is or is not a function. Not. No. It's repeated x's. That's the reason that it's not going to be a function. That's the one rule you got to follow to be a function, is to do that. Okay. So ordered pairs in a set, that's the little curly braces on the outside, and it's listing the ordered pairs. Could have a mapping to represent those. Could have a table of values, like the T table, with the X and the Y. Y'all seen that enough. We don't need to do an example like that. And then you could also have a graph, which is the more advanced way of things. So I'm just going to sketch a graph. You just try to make yours look like this. It doesn't have to be perfect. So I'm going to draw an X and Y coordinate plane, and I'm not even going to put any numbers on there. Then I'm going to draw a graph. Oops, let me change colors. So that blue line is my relation. That blue line represents all those ordered pairs that go with that. So does anybody remember a test for functions and graphs?
Vertical line.
Vertical line test. That is what we use for a graph, is the vertical line test. What are the rules for the vertical line test? All right, so how many times can it touch it and pass? Once. So anywhere you put a vertical line, it can only touch in one spot each time you lay it down. If it touches more than once, then it fails and it's not a function. So this one passes. This one is yes. It passes the vertical line test, so it is a function out of that. Get an example of something that maybe doesn't pass vertical line test. So I'm again just sketching an X and Y coordinate plane and sideways parabola there. Always a good example of one that doesn't pass. There is a place that I can lay a vertical line and it only touch once, right out there at the edge. But anywhere else I place that, it's going to hit the graph twice. So that fails the vertical line test. So this is not a function. Kind of that. Okay, so vertical line test. Anytime you got a graph, that's the best way to test for if it's a function or not is with the vertical line test. And you're just looking for repeated x values. So what that shows is there's an x value, the same x value there and there with different y values. That's what that shows. Okay. All right. So when there's a graph, that's nice. But what if they just give us an equation like this? Y equals x squared plus 3. So we've got to go on some information that we may already know. What do we know about x squared plus 3? Okay, well, more specifically, the name of that shape is what? A parabola, because it's x squared. It's quadratic. Done a lot of stuff with quadratics over Algebra 1 and Algebra 2 years. So we know that that's a quadratic, so we know what kind of shape it makes. So we can get an idea what the graph looks like. That plus 3 there would put it somewhere up there. It looks something like that. Now, does that pass the vertical line test? Yes. So this is a function. Now, here's another tool that you're going to have at your disposal since you've got a graphing calculator. If you've got an equation here, we can use the graphing portion of our calculator to help us build that picture. So I can just have x squared plus 3 and hit graph. Again, it's not something I necessarily have to have, but it's a nice tool when I do have that if I can graph that, I can see that. We knew already before we had the graphing calculator that it was quadratic and it made that shape. But that's always kind of nice when you can type that in and get the picture real quick. So that passes the vertical line test. Another kind of clue to that is to look at the x's and the y's. X's can have the exponents on them and be okay. Usually when y has exponents on it, then that causes problems. Okay, so like for example, y squared is equal to x squared minus 4. That's a weird looking problem. If we were going to graph this with either the graphing calculator or by hand, either way, what would we need to do first? Get y by itself. Right now, it's almost by itself. It's y squared, though. So how do we get rid of that? All right. So if I take a square root of y squared, what do I have to do on the other side? Take the square root of all of that, and what else? One very important thing. That when you solve by square roots, you have to put this in front of it. Plus or minus. Because the square, when you take a square root, it could be a positive 2 that gets you 4. It could be negative 2 squared that gets you 4. So you got to be careful of that. So the plus or minus. So we have two equations that we're graphing. We got the positive x squared minus 4, and then we got the negative x squared minus 4. And we could go through the steps of picking some x values and plotting points, getting some ordered pairs and making points out of that, and get an idea of what's going on, and get the picture. I'm going to graph it with the graphing calculator and kind of just show you what's happening there. So square root of x squared minus 4, and then y2, I'm going to put negative square root of x squared minus 4. And graph those together, and we see they're different colors, but they go together. The whole graph is one piece. That's the vertical line test. Definitely not. Definitely would fail it in lots of places. The key to knowing that without the graph is the fact that the y and the x are both got exponents on it. That's the shortcut to it. Know that you can graph things and decide that, but this is not a function because of the fails vertical line test, but also because x and y are both squared. So it's not a function. So just determining if something is a function, if it's a set of ordered pairs or a mapping or a table, x's can't repeat. You just look for repeated x values. If it's a graph, we're doing a vertical line test. That's pretty much it for that part of things. Now, let's get into function notation, which you've seen before. Nothing new. Function notation, that's that f of x stuff. What's f of x the same thing as? Y. Y'all know that? Nothing new. So when we look at problems, we'll start with something super easy. 3x plus 5. When it has that notation on it, they're telling us it's already a function. That it passes vertical line test. They're telling us, hey, this is a function. We're going to use it, okay? And then what they'll ask us to do is find the function value. They'll say find f of negative 5. Well, how do you do that? Yeah, you plug negative 5 in for x. So f of negative 5 means 3 times negative 5 plus 5. So that'd be negative 15 plus 5, which is negative 10. So f of negative 5 is equal to negative 10. That connect the ideas between the function notation and that this is also an ordered pair, negative 5, negative 10. Those are the same things. Okay, when you have function notation, that's the same thing as an ordered pair. Okay, when you plug in a value for x, that's the x value of the ordered pair. What you get as an answer is the y value of the ordered pair. Connect those two ideas together because they kind of mix and match it in the as you'll get into this textbook, you'll see they use notation a lot. And if you understand the relationship between ordered pairs and function notation, the notation doesn't bother you as much. So understand that that's just an ordered pair is all that is. So be careful of that. Let's do a little bit more algebra. Get our brain going with some algebra stuff. So f of x, let's do a different function this time. Let's do 2x squared minus 3x. And let's find f of 2x. Because everybody needs to do a little algebra early in the morning. Get going with that. So this one, they're asking us to take something that's not just a plain number and find the function value. So when we work this out, we're not going to get just a plain number at the end. We're going to get some sort of algebraic expression out of that. But that's okay. That's part of an algebra class is being able to do that. So let's take that and work it out. So what do we do with the 2x? Put it in everywhere there's an x. And now, order of operations tells us what has to happen first. You got to square the 2x. So how do you square 2x? It'd turn into 4x squared. So that's 2 times 4x squared. And I'm just doing this one step at a time. Obviously, I'd hope that you do more than one step at a time as you're doing this. But so I'm just writing it out. Okay, now what? Just multiply it out, right? It'll be 8x squared minus 6x. Are those like terms? No. So we always look for like terms and see if we can simplify any. We can't. So that is our final answer for that function value. Okay. So plug it in something that's, a little bit different. Let's use the same function. 2x squared minus 3x. And let's find f of negative x. Sometimes when you throw that negative in there, it it causes some issues, so I want to make sure that we pay attention to those things. So again, it's the same old story, just a different version here. 2 parentheses negative x minus 3 parentheses negative x. What's really in front of that x? A -1. So maybe that, if that helps you, you're welcome to put it there. It doesn't necessarily have to be there, but it's there, so maybe it helps. So what happens when you square -1x? It means positive 1x squared. So 2 times positive 1x squared is going to be 2x squared, right? What about the next piece? Yeah, they end up being plus 3x is our signs. And then there is our function value out of that. So there is plugging in a -x. That's going to come in handy here the next section or two. That's one of the tests that we'll do. But being able to find that function value is important. All right. And then sometimes they'll do something weird to you, and they'll say, here's your function, 2x squared minus 3x, and they want you to find negative f of x. It's not really function value, but it's just a different take on the function. What does that mean? Well, what if they did this? Find 3 f of x. What would that mean? Not divide the whole thing by 3. You're going to multiply it all by 3. So up here, you're going to multiply it all by -1. So negative f of x, it just changes the sign of everybody. So that'd be -2x squared plus 3x. And it just changes the signs of everybody. On this one, it's multiplying everybody by 3, the whole problem. So that'd be 6x squared minus 9x. That's what 3 f of x is. So just some manipulation of functions using just some multipliers out of there on the outside. So you're not plugging in anything in the place of x for these. You're manipulating the coefficients. Let's do a good Algebra 1 kind of problem here. Find f of x plus 2. That's a good Algebra 1 problem. So are we plugging something in for x this time? Or just manipulating the coefficients? I think we're plugging something in this time. So when we plug that in, be careful. Because when you square x plus 2, if you get x squared plus 4, you're wrong. What's it mean to square x plus 2? Yeah, you're multiplying out x plus 2 times x plus 2. And if you need to write that out, that's fine. I'm just going to go ahead and multiply this. So I'm multiplying x plus 2 times x plus 2. So that's going to be x squared plus 4x plus 4. And then multiply that answer by 2. So it's going to be 2x squared plus 8x plus 8 minus 3x minus 6. So good old Algebra 1 problem, because there's a lot of simplifying, a lot of multiplying and stuff to do. We can simplify that out. Like terms, got the 8x and the minus 3x. It'll be plus 5x. 8 minus 6 would be plus 2. For f of x plus 2. It was that quadratic there. Be careful on the simple algebra stuff. I know you guys know how to do it. Just don't make simple mistakes because you got in a hurry and you're not paying close attention to detail. That's normally the most common mistake on that kind of stuff, is just getting in a hurry or making a simple arithmetic mistake instead of paying close attention to that. All right, I'm going to show you how to do function value for a number with the graphing calculator. I'll show you how to do that. It's really kind of a handy thing. It might help you some on ACT. I know some of you will be taking the ACT this spring. Some of you might be taking it in February. I'm not sure if you've signed up for that or something. But so it's kind of a handy thing sometimes to be able to plug in using the graphing calculator. Again, it's one of those things where you don't have to do it with the graphic calculator, but it does have that functionality. So I'm gonna show you how to do that. So with the TI-84, and some of you already know how to do this. F of x, and we'll just do a different one. We'll do 3x squared minus 5x plus 7, and we're going to find f of 1.25. So with the graphing calculator, there's a couple of different ways to do it. I'm going to show you with the y equals menu, and I'm going to show you both ways, but both are about the same as far as that goes. So with the y equals menu, you can go to y equals, and I'm going to clear out this other junk that I had in there. And I'm just going to type the equation in there, 3x squared minus 5x plus 7. And then I'm going to hit second graph to go to the table. And I've got my table set up to where I can type in the value that I want. I want 1.25, so I'm going to type in 1.25 and hit enter. And it'll give me back that solution there. That works. If your calculator is not set up to be able to type those in, the way to set it up is to hit second and then window. Window is the one that's in red there. And make sure that your independent is set to ask. Once you set it to that the first time, you won't have to go back and reset it out of that. A lot of you probably already have yours set that way because we set it that way in Algebra 2, and you probably hadn't changed it back. So make sure the independent is set to ask and the dependent is set to auto. Independent is your X value, the dependent is the Y value, and that will allow you to type in whatever X values you need. The other way of doing it is to actually store the 1.25 as X, 1.25, and then right here above the on button is the store button, and I'm going to store that as X. And every time I type an X on the regular calculator screen now, it's going to think, oh, that's 1.25. That's what the calculator remembers. So then I would just type in the problem, 3x squared minus 5x plus 7. Notice that's the same number that I got on the table. Okay, either way works. If you're going to have to do a bunch of values for the same equation, the table way is the best way. If you're just doing one single value, then this might be the quickest way. It doesn't matter either way. You could also just plug it in and type it in 1.25 squared and times 3, and then minus 5 times 1.25. So 5.4375 is the answer to that. Okay, and because we had a decimal in the beginning, we have a decimal in the end of the answer there. Okay. All right, so that gets us through the kind of the basics of functions and a lot of things that we've done before. So let's get into maybe the meat of this lesson, or what I think is the biggest part of this, and that's the domain of a function. So very important part here. The domain of the function are the x values that quote unquote work for a function. Okay. When I say work, I mean these are the X values that don't cause issues, and there are certain kinds of issues that can come up with domain, but domain starts with all real numbers. And there's different ways of saying all real numbers. One way is X, such that X is an element of the real number system. So that element is the Greek letter epsilon. It's like a lowercase c with a little stick in the middle. That's all that's how you make that symbol. Is make a lowercase c, then put a stick in the middle. And that's the Greek letter epsilon. It just means it's an element of that set. And that R, what I did is you just do an R and then put an extra bar on the outside of it. This is the set notation for all real numbers. Then we're going to get into interval notation. Interval notation for all real numbers is negative infinity, positive infinity. We're going to work with both of the set notation and the interval notation throughout the course, so being able to bounce back and forth with that. Some of you that had Algebra 2 last semester, with me, we've done a lot with interval notation already, so you're not going to have quite as big a learning curve as some of the folks that had Algebra 2 before. We didn't do quite as much with interval notation when they had that. But it's not a hard thing to pick up. You're going to pick it up pretty quick, and we'll bounce back and forth between those, okay? So everybody starts with all real numbers as the default. So if there are no red flags, and we'll talk about the red flags in just a second, then the domain is going to be all real numbers. Okay, so red flags, it changes. No red flags, it's all real numbers. So let's look at what red flags could come up. So the red flags that come up are x's in the denominator. What's the only number that we cannot divide by? 0 is the only number that we're not allowed to divide by. That's an undefined operation. So the x is in the denominator. So if you have an equation and there's x's in the denominator, then you could have a division by 0 issue, and we're going to talk about how to work with that. The other red flag, there are only two that come up. Square roots. When you take a square root, what kind of number makes the square root do something weird? Negative. That's where we get into that complex number system with the i's and stuff like that. So when we're dealing with functions, we only want to talk about the real number system. We don't want to get into the complex numbers because they don't show up on the graph. If you remember from Algebra 2, when we talked about functions and it had a complex solution, it didn't show up on the graph. It didn't cross the x-axis there. Same idea here. We're going to look at the real numbers solutions to that. So when we're talking about square roots, we want 0 and positive only. Okay, those are the only two red flags that can cause issues with the domain. So there's not many to even look for. So if those two things don't show up, the domain is automatically all real numbers. Okay, so if those two red flags aren't there, either of them or both of them, then you're going to go with all real numbers for your domain out of that. It's not super complicated. Now, let's look at some problems, and we're going to our job is going to be find the domain. Example O. Let's start with something super easy. A good old quadratic, because we're used to those. Done a lot with them over the years. X squared plus 5x minus 7. We look at that function. It's in function notation, so we know it's a function. we look at that and we say, okay, are there any red flags? Do either of the red flags that are listed there, do they show up in that problem? No x's in the denominator. There's not even a fraction in that problem, so it can't be an x in the denominator. So that one's out. Are there any square roots? No, there's no square roots. There's no x's in the denominator. So we know automatically that this one has a domain of all real numbers. So in set notation, we're going to write that as x is an element of the real numbers. In interval notation, spell interval right. I-N-T-E-V-E-R-V-A-L. In interval notation, that's negative infinity to positive infinity. That's the domain for that function. No red flags. So the domain's automatically that. Everybody starts there. We carve out the parts that we don't need. Okay, let's look at this one. Call this one g of x, just a different name for a function. 5x over x plus 3. Do either of the red flags come up in this one? Well, that thing's a big old fraction. Are there any x's in the bottom? Yes. That's where the problems can happen, okay? So in Algebra 2, we called these excluded values. Y'all remember doing that? Some of you that had it last semester, it'll be more fresh on your mind. Some of you that had it last year, it may not be as fresh. But excluded values are the things that mess up the denominator. And remember, what's the only number we cannot divide by? 0. So what makes the denominator be 0? So we set x plus 3 equal to 0. The denominator is the only part that could be a problem. So we're going to set the denominator equal to 0 and solve it. So that's an easy solve. That's negative 3, right? If x were negative 3, it would make the denominator 0. And you can't divide by 0. So that x value is the one that has to be thrown out. Okay? So this is an excluded value. So we're going to exclude it from our domain. So then I'm going to show you how to do that. So in the set notation, x, and then the straight up and down bar, that's all x's such that x does not equal negative 3. That's the set notation. Now, with interval notation, the way it works, and I think one of the best ways to explain this is with a number line. So I got negative infinity down here and positive infinity up there, right? So that makes sense. Go to the left, you go into negatives. Go to the right, you're going to positives. Negative 3 is somewhere in the middle here, right? I'm just going to put a negative 3 there. So negative 3 is the only number that can't be used. So when you're writing your interval set, you're going to start at negative infinity, and you're traveling along. Everything's going great until you get to negative 3, and we're skipping that one. So we got to leave a hole there. So we got to stop at negative 3. So we're going to put negative 3 after the comma. And then put another parenthesis, and then a U for union, because union joins two sets together. And then we're going to start right after negative 3 and go on up to positive infinity. So negative 3, positive infinity. Okay. That is how you skip a number in interval notation. Okay. Interval notation is actually a little bit more descriptive than set notation in that it tells you all of the things that work, where set notation only tells you the one thing that doesn't work. So they both say the same thing, but interval notation is just a little bit more information in it there. So, but interval notation, parentheses are always going to be on the infinities. And if you're not using the number, like this case, we're skipping it, then you're going to use parentheses. If you're using the number, and we'll see that when we get to the square root stuff, then you're going to use a square bracket, and I'll show you that in just a second. Okay, so let's do another one here. This function, let's do 12 over x squared minus 16. I'm going to find the domain. That's all we're doing. What red flag comes up? X in the denominator. That's the problem. So what do we do with the denominator? Set it equal to 0 and solve it. How can we solve that? What ways? Difference of squares, factoring would be a good way. What other way could we do it? There's two different. Square roots would work as well. So either way, doesn't matter on this one. I like the difference of squares because I like factoring. So x be 4 and negative 4. So we got two numbers that we're excluding for this one because there were two answers that made the denominator equal 0. So we're going to exclude two numbers. So the domain in set notation, that's the easy one. You just put them, list them out there. X cannot equal, or X does not equal. That's just an equal sign with a slash through it. Negative 4 and positive 4. I usually put mine in numerical order, but there's no rule that says you have to. But that's the way you're going to see them most of the time. Now, the interval notation is a little tougher on this one just because it's longer. So when we're doing our interval notation, we're going to start at negative infinity. What's the first number that we'll come in contact with that we have to skip? Negative 4. So we're going to skip negative 4. And then we're going to pick back up right after negative 4. And then what's the next number we're going to get into that we got to skip? Positive 4. We'll skip it. After positive 4, where we're headed? To positive infinity. So there would be the interval notation for that. So we've skipped two numbers there. They don't usually get much more complicated than that. That's really about as tough as they get in this section, as far as finding the writing the domain and interval notation. So there we're skipping negative 4 and positive 4, and that's the interval notation for being able to do that. Okay. Just going to take a little practice getting used to the interval notation if you're not as comfortable with it as some folks will be. Let's look at this one. F of x is equal to the square root of 2x minus 6. Square root of 2x minus 6. Is that a red flag? Yeah, got a square root with an x inside of it. So that's going to be a red flag. Now, what kind of numbers have normal square roots? Positive and what? What other number that's not positive or negative has a normal square root? 0. Square root of 0 you can do, right? But if we get into the negatives, that's when the I thing comes in. So we need to find out when does this have a normal square root. So what we do is we take whatever's inside of the square root and set it greater than or equal to 0. Set up an inequality and solve it. Pretty easy thing there. Let's get old algebra 1 or pre-algebra, really. X is greater than or equal to 3. Those are the numbers that work. Okay, so the difference in this and the denominator thing is we were looking for numbers to exclude with the denominator. With the square roots, we're looking for what numbers do work. So this tells us what numbers do work. So the set notation for the domain is going to be exactly that inequality. All x's that are greater than or equal to 3. Okay, greater than or equal to 3. Now the interval notation, I'm going to go back to the number line idea. Where's the lowest number that would work here? 3. Do we include 3?
Wait a minute.
Yes, it has equal to, right? So I'm going to use the bracket, square bracket, and I'm going greater than 3, so I'm going this direction. So the interval notation for that is square bracket 3, positive infinity, and put a parenthesis on it. Square bracket means that we're including that number. Okay. 3 is getting used, so we're going to put a square bracket on it. And those would be our domains for that function. All right. Square root of 8 minus 2x, and then a plus 7 on the outside. What happens with this one? Does the plus 7 affect the domain? Does it have x?
No.
No, so no, it really doesn't affect the domain. What part is the red flag coming from on this one? The square root stuff, right? So that's the only part that really matters, is where the red flag shows up at. Okay, so we're going to take that part and do what with it? Set up that inequality, greater than or equal to 0, and solve it. Subtract 8. Negative 2x is greater than or equal to negative 8. Divide by negative 2. That'd be 4 over there. What happens when I divide by negative 2? Flip the symbol there. Kind of makes sense that we were doing that with Khan Academy yesterday, right? Now, set notation, that's the easy one, right? You just copy it. Now let's get that interval notation. All the x's that are less than or equal to 4. So what's the smallest that I'm using? Negative infinity, because it's everything that's less than negative or than positive 4. So I'm going to start at negative infinity. And where do I stop at? Positive 4. Do I include the 4? Yes, so bracket on that. And there's my domain. Not bad. Again, the only red flags that exist are x's in the denominator and then square roots. Let's get crazy. All right. So we got f of x is equal to 3x over the square root of 5 minus 2/3 x, and then a plus 4 on the outside. What's up with this one? Got a lot going on. It does have a lot going on. How many red flags do we see? 2 of them. Both of them are in this one. The denominator has a square root in it with an x inside of it. So you've got a denominator and a square root there. So when we look at that and think about finding the domain, we're going to set 5 minus 2/3 x. If it's just a square root, we set it greater than or equal to 0. But because it's in the denominator, what changes about that? What part can it not be? It can't be 0. So what does it have to be? Greater than 0. So just a greater than symbol there. Because we lose the equal to because it's in the denominator of a fraction. Does that make sense? Remember, the denominator of a fraction, you can't have x being equal to 0. So we lose the equal to mark because that square root was in the denominator. So that's the kind of the weird thing about this. But then that doesn't look too complicated. That looks doable. I can solve that. So let's solve it. Minus 5 is 2/3 x greater than -5. How do I solve that? Multiply by -3/2. Flip the symbol. That's going to be positive 15/2. That's not bad. All x's, as long as x is less than 15/2. And then in interval notation, what would that be? Parentheses after the 15/2. That's right. Good job. There's our domain. So it looked really, really complex there, but it really ended up turning out not to be too difficult. That's what I want you to understand, that this, if it's getting really, really complex, you might be doing something wrong. This is not going to be just crazy hard kind of stuff that you're setting up your equations or inequalities to solve. All right, one last thing before we finish for today is function operations. So let's get a couple of functions here. F of x is equal to 3x minus 5, and g of x is equal to 5x minus or plus 1. And we're going to check real quick, see what I think it actually I'll make sure. So we're going to work out the operation and find the domain. So find the operated function and domain. All right. So what's this example? U f plus g of x. All right. So we got those two functions up there. F plus g of x just means do what with them? Add them together. So we're going to take f of x, 3x minus 5, plus 5x plus 1. Technically, if you want to put them in parentheses to show the two separate ones, that's fine. You don't have to with the addition. It's not going to be an issue. And how do we add those two together? Just like terms. It's really is that easy. 3 plus 5x. 3x plus 5x is 8x. -5 plus 1 would be -4. So there's our operated function. What's the domain of that function? All real numbers. So that's going to be, that is the set notation, interval notation is that. Let's do the subtraction operation. Same two functions, f minus g of x. So you just take 3x minus 5 minus 5x plus 1. I think parentheses are a little bit more important here because of the subtraction, because you're subtracting that entire function, 5x plus 1. So when you subtract, you got to subtract 5x and subtract 1. So again, it's like terms, nothing new about that. Really easy to do. So the -2x minus 6 is the operated function. What's the domain? All real numbers. No red flags showing up on that, right? So that's nice. So All x's, as long as x is an element of the real numbers. Negative infinity to positive infinity. That's nice. Do f times g of x. Same two functions, just multiply. 3x minus 5 times 5x plus 1. Double distributive property. That's all you're doing is multiplying that stuff together. 3x times 5x, 15x squared, plus 3x minus 25x minus 5. So I'm just distributing 3x to everybody and then distributing minus 5 to everybody. And then combine like terms. And there's our operated function. What's its domain? All real numbers. Because there are no red flags in that operated function. Okay. One more operation to do. F divided by g of x. Same two functions, 3x minus 5 over 5x plus 1. Is there anything I can do to simplify that? No. Neither of those factor at all. So I'm done. That's my function. But what's my domain? Yeah, I got to set the denominator equal to 0 and solve that out. And that's going to carve out a number. 5x plus 1 equals 0. The x equals negative 1/5. So our domain, x cannot be negative 1/5, right? What is the interval notation for that? Negative infinity, negative 1/5, parenthesis, negative union, negative 1/5, positive infinity. That's it. So the operation, that's the easy part. When you get to the final answer there, look at it and see if there are any red flags. If there are, take care of the domain the same way we did with the others. No different out of that, just doing those operations. All right, so the suggested problems for this section, I'll scroll back up so you can still see that, are on page 216 in your textbook. I suggest the odd ones, you have the answers to the odd ones in your textbook. If you have trouble with the odd ones in a certain section or certain subpart, then the even ones beside it are the same kind. And I have my textbook up here that has the answers for the even ones in it as well. So the idea is to make sure that you can do all of those kinds of problems. Tomorrow will be a work day in here, so you'll have tomorrow to work on this and ask questions and all that sort of stuff. And then on Friday, we'll have our first quiz at the beginning of class over section 1, and then after that quiz, we'll do notes for section 2. Come in ready to work tomorrow. If you need a graphing calculator, make sure you get your contract signed and bring your money in. We'll get that.